Well, good morning and welcome to the first press event of the day, our Geoscience Grab Bag number 3. With us today we have Riley Finnegan from the University of Utah talking about rock arches. And we have Matthew Wielicki from the University of Alabama who's going to talk about using geology to study kidney stones. I'm going to turn it right over to Riley to get us started.
Hi, I'm Riley from the University of Utah, and I will be talking to you today about how different rock arches and towers vibrate in response to sound produced by helicopters. Our key findings from the study is that helicopters produce something called infrasound, which is really low frequency sound. They produce it, a common two-blade helicopter will produce infrasound at 13 hertz, which is far too low for a human to perceive, but we've measured quite high powers. So some of our recordings of helicopter infrasound are up to 100 decibels, which is like being at a live concert, but it's kind of weird because you cannot hear it because it's such a low frequency. This infrasound has been able to cause different arches and towers to resonate at vibrations that are 100 times stronger than they typically do. And some studies have shown that towers can vibrate at potentially damaging levels. Some of the determining factors for why an arch or tower might vibrate include or vibrate in increased levels to helicopter infrasound is the size of the arch, the shape, and the stiffness of the arch or the material makeup of it, as well as the distance, the speed, and the number of blades of the helicopter. You might be asking, why should we care about arches and towers, and why should we be concerned about helicopters? In Utah, arches are a very culturally valuable resource. We have over 6,000 documented around the state, an entire national park dedicated to how great these features are. Additionally, Native American groups in the Southwest Desert region consider arches sacred, and so we want to make sure that we aren't inadvertently affecting the health of these really precious features. Helicopters, as I mentioned, produce sound energy, and they can fly nearly anywhere, so the reach of their energy is pretty much unlimited. Over the national parks in Utah, there are thousands of helicopter flights each year just for tourism, and the Grand Canyon sees hundreds per day. So this is really, helicopters fly everywhere pretty much all the time, and their sound is traveling with them. Our study was flying helicopters at 6 different flights around Utah and measuring the vibration response of 11 different rock arches and towers to the helicopter sound energy. This is Little Egypt highlighted in orange on the map, and it's an outcrop of some small towers called hoodoos, and we measured the vibration response of 6 of those towers. And then I've also highlighted Arsenic Arch in pink. I'll give an example of how an arch might vibrate more from exposure to helicopter noise. Arsenic arch is, you can consider it kind of any arch, kind of like a guitar string. If you pluck the guitar string, it will vibrate at a certain frequency, so it'll produce a tone. That's something you hear. And it's the same thing with an arch. If you, the earth is constantly plucking the arch, and so it's vibrating from energy within the earth and around the earth, and it naturally vibrates at 6 hertz, at 16 hertz, at 26 hertz, and 36 hertz. And the animation is of the 26 hertz resonant mode of Arsenic Arch. And of course, this is an exaggeration. It's not actually shaking that much, but it gives you an idea for how it is shaking. And this is happening every single second, every single day. And 26 hertz happens to coincide with one of the frequencies of sound emitted by a helicopter. So helicopters emit, like I said, a 2-blade helicopter will commonly emit a frequency or sound at 13 hertz, and then it has higher overtones, such as like at 26 hertz. And if you coincide the frequency of incoming energy with the natural frequency of an object, that object will often vibrate more. It's kind of like if you properly time your push of someone on a swing, and so you have the right frequency of pushing the person on the swing, they will swing higher and higher. And that's the same idea. This is a vibration recording of arsenic arch during a helicopter flight. So the top panel is the vibration velocity of the arch over time, and the bottom panel is a spectrogram of the vibrations as well over time. So spectrogram essentially shows you power, which is different colors, at different frequencies, which is on the y-axis over time, on the x-axis. And as a reminder, this is a vibration recording, not a sound recording. We sped up the vibration recording 20 times, so it's something that you could hear, but just a reminder that it is vibration, it isn't an audio recording. And it's a little spooky, so we'll give it a proper listen. You'll hear it get louder, the vibrations getting stronger as the helicopter approaches and as the helicopter flies over. So we'll play it now. Kind of fun, kind of weird. This is another example of an arch called Two Bridges. It's in Bryce Canyon National Park, and it naturally resonates at about 13.5 hertz, which coincides with the lowest frequency of sound emitted by the tourist helicopter that flies over the park up to thousands of times a year. We scheduled just a standard tourist flight to happen over the park, and the closest that the helicopter ever gets to the bridge is 600 meters away. Yet we see an increase in the vibrations of 100 times, which is quite a lot for the helicopter being so far away. The amplifications don't reach a level that the vibrations don't reach a level that we would consider instantaneously damaging, but this is something that the helicopter might experience 100 times a year, like on a really gusty day. We'll give it a listen as well. As a reminder, that was a vibration recording, also sped up 20 times. Squint arch is the last example I'll work through. It also resonates around 13 hertz, and it's perfect for increasing vibrations or having its vibrations increase from a helicopter. So we flew a helicopter in a bit more controlled way, flying over it, as well as approaching the arch in incremental in a stepwise manner. And so the first part of the vibration recording that you'll be listening to is during the flybys. And so the amplifications again spike, and then at the end, the helicopter is approaching the arch closer and closer, and you'll hear the amplifications, or the vibrations amplify more and more. So this arch reaches 0.1 millimeters per second, which is an order of magnitude lower than what, again, we would consider instantaneously damaging. But this vibration is something that naturally the arch would experience maybe once in 100 years. And so it really is a concern still for the long-term effects that a helicopter flight would have on the health of this arch. This has also been sped up 20 times, and it is a vibration recording. Let me tell you, when I was in my office making this presentation, people were turning around all the time. What is that? So the general takeaways from our study is that helicopters can cause arches and towers to shake stronger than they typically do, and that our tests specifically have not generated vibration levels that we would consider instantaneously damaging, but the long-term effects of helicopter flights is still a concern that we have for the general health of these really special features that we have. Thank you.
Oh, that's not my first slide. Is it possible that that's not my first slide? Which is okay.
They transferred it, so maybe we dropped something. Okay, yeah, he accidentally dropped the slide, so there you go.
Great, thanks. My name is Matthew Wilecki. I'm an assistant professor at the University of Alabama in the Department of Geological Sciences. And I'm going to talk to you a little bit about our work on kidney stones. Before I get into it, I'll address a concern or a question that many of you probably have already, is what are earth scientists doing looking at kidney stones and getting involved in medical research? And to address that, I'd like to highlight these growth bands that you can see on this image here on this first slide. That's a kidney stone that was reported on by one of our collaborators and co-authors on this research in an article written last year. And I just want to highlight those growth bands that you can see on the outer edges of that. And those are very analogous to sedimentary bands in a stratigraphic package, or in growth rings and any other sort of chemical mineral that grows in a whole host of geologic environments. And so what we're trying to do is use some of the tools that earth scientists have developed over many decades as they analyze these types of mineral deposits that grow in nature, and use this toolkit to investigate human kidney stones. In fact, they are stones, so we can use a lot of the same types of techniques that we use for natural geologic samples to investigate these human kidney stones. In particular, what we're going to do is apply some novel techniques like atom probe tomography. This was the first time any atom probe tomography has been done. I'll explain that technique in a second. I'm just highlighting the data set right here that I'll explain to you in a second, as well as transmission electron microscopy. And before I get into both of those techniques and what those are telling us, I just wanted to show you an image of our kidney stone that didn't load. That's okay. You can kind of see in this broken image, hopefully we'll upload a better one that the media can use, but you can see in this upper portion that there are some of these growth bands. And that's what we're starting to investigate. So we're taking that kidney stone there that was provided to us from the Mayo Clinic, from a patient, and starting to work our way down into the atomic layer scale. So I'll highlight some of these scale bars here. You can see on the image on the middle left, there's a scale bar there that's 100 microns. That's about the width of a human hair, to put it into context. And so what we're doing is we're removing very, very tiny portions of this kidney stone so that we can start to investigate this material at the atomic scale. And so there's a lot of work that goes into just the sample preparation. Every material is unique and behaves differently. So there's been a lot of work that has gone into this, and there is going to be a lot of progress that's made as we learn how to handle this material better. So here's some of the results. So this is the first atom probe tomography results on a human kidney stone. So atom probe tomography is a technique that allows us to essentially get some chemical information as well as information on where those atoms exist. So we can reconstruct a three-dimensional reconstruction of the chemistry of that object. And so what we're reconstructing here is our kidney stones. We're looking at things that are on the order of 1/1000th the width of a human hair. We get a mass spectrum, so we know what the chemistry of the elements is, and we have some information about where the elements exist, so we can reconstruct this. The transmission electron microscopy gives us chemical information as well. On the picture on the right, you can see an image that has of our kidney stone, and it's zoomed in, so that is a scale bar there of 300 nanometers. So we're talking on the order of 1/1000th the width of a human hair. And we get some chemistry information. The overlay there is some of the chemical constituents that we're interested in and how they vary on that nanometer scale. And then we try to get some structural information from transmission electron microscopy as well. There's still a lot to do in this. This is very early results. We're not getting a lot of information on the structural side at the moment, likely because we still don't know exactly how to prep the sample so that it's conducive to this type of technique, but we're still making some progress there. And why is this significant? So the significance of this research is that kidney stones affect about 9% of the US population and about 12% of the world population. So that's nearly 1 billion people suffer from kidney stones. And currently there's really no in vivo treatments. The treatments for kidney stones currently are sonication and passing the stones or invasive surgery. And we think that if we can understand how these stones grow and are constructed on the atomic scale, that will be a foundation for developing in vivo treatments on how to deconstruct these stones within the kidneys and to promote an environment in the kidney that is conducive to resorption of the stone, to hopefully reduce the amount of invasive surgeries and passing the stones. So I love to take all the credit for this, but obviously this is a whole host of academic institutions and the Mayo Clinic that help us with this. We have a poster tomorrow at 1:40, so please come by and see the poster if you're interested to get some more information. Thank you.
Well, thank you to our panelists, and we can take a few questions from people in the room. Yes, we usually open it only to reporters, but, well, let's go with Harvey first.
Harvey Lyford, freelance. Although I once had a kidney stone, the question is for Riley. I was in Utah in September visiting Arches National Park and Bryce and others you mentioned. So I was really interested in this. Is the National Park Service concerned at all? Are they aware of your research? Has there been previous suggestions that helicopters may be causing long-term damage?
So does this work? The original question was posed by the Native American Consultation Committee, which is a consultative organization of 6 different Native American groups in the Southwest Desert region that partner with the National Park Service in managing Rainbow Bridge National Monument. So they pose this question of do multiple helicopter flights every single day over many years have can that damage Rainbow Bridge National Monument? And so we took this question a little bit further of not just Rainbow Bridge, but can this affect other rock features as well? And we don't, or I guess we have a permit to work in most of the national parks. However, our testing was done mostly on BLM land, where I think the requirements for permits are a bit less. So I'm sure they have similar concern. However, they don't manage the airspace above the national parks. So.
Larry? Yeah.
Yeah, hi, I'm the social media guy for AGU, but I'm just very interested in both. For the Riley, is there anything that pilots can do? You mentioned certain frequencies that are particularly affect the bridges and different things. Is there anything pilots can do to change the speed of their blades or anything to mitigate this?
So helicopter rotors rotate at the same RPM. That doesn't change. However, we learned that directionality is really important. It depends on the feature, though. So some features might be relatively unaffected by horizontal incoming energy, whereas others might be unaffected by energy coming in at an angle. So it really just depends on the feature.
And the other question I had regarding kidney stones is, was it difficult for you to do this? Did you have to kind of come into it and not think about the medical side and just try and stay in the geological mindset when you did this?
Yeah, that's right. So we're definitely approaching this from a thermodynamic standpoint and stability of a mineral, just like we would in a geologic environment, and kind of removing ourselves from the medical side. Eventually, the goal would be to merge those two, to start thinking about certain conditions that are more conducive to kidney stones, like diabetes and other metabolic disorders. But currently, we're just trying to really understand the physics behind how these things grow and the chemistry, and then we can start approaching kind of bringing in more information like medical history and things like that.
Just checking if we have any questions online. Just a moment.
Catherine Wright of Physics Magazine has a question for Riley. She wants to know, how did you pick the 11 arches that you studied?
We study a range of arches of different sizes and shapes and in different locations, and maybe a few dozen at this point we have measured the resonant frequencies of. And so we chose ones that had natural frequencies that would likely coincide with the sound emitted, or the frequency of sound emitted by helicopters for these particular tests.
Any further questions from the room? All right, I'm going to thank our panelists, and we're resuming with the Parker Solar Probe at 10 a.m. also advance on the keyboard.
Okay, with the arrows.
With the arrows. Okay. Yeah. Mics will be live when you answer questions.
Okay.
All right. Good morning. We're going to get started with our 10 o'clock press conference, New Science from NASA's Parker Solar Probe mission. First speaker will be Nicolene Weil from NASA Goddard Space Flight Center. We'll have Tim Horbury from Imperial College London, Kelly Corrick from the Smithsonian Astrophysical Observatory, Nathan Sweden from Princeton University and the University of New Hampshire, and Carl Bettams from the United States Naval Research Academy. I'm going to turn it over to Nicolene.
All right, well, hi everybody. I'm Nicolene Weil from NASA's Goddard Space Flight Center. And we're all here to talk to you today about Parker Solar Probe and some of the new exciting results that we've gotten. Parker Solar Probe is the closest human-made object to the sun. It's gotten closer than any human-made object has ever gotten before. It's already flown inside the orbit of Mercury and is sampling material closer than any spacecraft ever has before. So here, what we're looking at is an artist's rendition of the sun and the material that flows off of the solar atmosphere out into the solar system. We call this material the solar wind, and it fills the entire solar system. It bombards all of the planets, including Earth, and it interacts with Earth's magnetic field. Here we're looking at Parker Solar Probe data, WHISPER data. Let me see. There we go. All right, we're looking at WHISPER data. We're looking at the density of this solar wind, of this material that's filling the solar system, but we're looking at it up close. Parker Solar Probe also has in situ instruments that measures directly this material as it's flying through it. And we can see some structure in the density, in the solar wind, that we're seeing now at a level of complexity and detail that we've never seen before. And those details give us information about how this solar wind was formed, the processes that happened back at the sun that create it. Details that we've had hints of before, but we've never seen so close. We're also using information from all of our other telescopes and spacecraft to really piece together the full story of what it is that Parker Solar Probe is flying through. So here I'm showing an orbit of Parker Solar Probe in orange around the sun in the center. Earth is here in green, and one of our spacecraft stereo is over here in red. And so you can see by looking at what's coming off of the sun from Earth and also looking at what's coming off of the sun from stereo, we can really see what it is that Parker Solar Probe is flying through. So here's a movie of, again, the density, this solar wind density, this material coming off the sun, from stereo, and we see Parker Solar Probe flying through it. So by looking at the up-close details with Parker Solar Probe and comparing them to this global picture of what stereo is seeing, we can really paint a full picture and understanding. Here's that same set of images of density from the stereo spacecraft, but now there's been a lot of processing done to the images to really pull out some of these little tiny details, some of these small features in the solar wind that give us hints about how the solar wind is formed. Again, because we've flown through it with those in situ measurements, we can really understand some of the details that we've only had hints at before. So this matters because it's telling us about fundamental physical processes as this material is created and sent out into the solar system. It also matters because of the connection between the sun and the Earth. Even though these structures are small in this movie right here, they're actually large compared to Earth and Earth's magnetic field. This is another another artist's rendition of Earth and Earth's magnetic field, and these structures as they pass by. And because they're density structures, they actually squeeze Earth's magnetic field and release it. They drive dynamics in Earth's magnetic field and Earth's radiation belt on a regular day. They're not the big dynamics that we're going to hear later on, but they're the ones that are there every single day. So it's really important to understand how these things are made back at the sun and what they look like when they get to the Earth. Next, we're going to hear from Tim Horbury, who's going to talk about other kinds of structures that we see in the solar wind.
Thanks a lot, Nikki. Hello, everybody. My name is Tim Horbury from Imperial College London. So Nikki's told you about how Parker Solar Probe going close to the sun is revealing a lot of fine-scale structure that we haven't seen before, and I'm going to talk about things on even smaller scales. So the measurements that Parker is making of the magnetic field and the plasma environment around the spacecraft have revealed an enormous array of phenomena on very small scales. I can't talk about all of those today. I'm going to talk about one in particular. So on the left-hand side, you can see a picture of the sun in ultraviolet light, and this is showing us a picture of the atmosphere of the sun, and the glow there is because of the very hot plasma environment. And you can also see dark patches here. These are called coronal holes. And there was open magnetic field coming from those coronal holes, and the plasma flows off into interplanetary space at very high speeds, hundreds of kilometers a second, in a very smooth, constant flow. Now, we've known about these coronal hole flows for a long time. We can measure them in interplanetary space near the Earth, for example. But the models that we have of those don't explain the speeds that we see. So we understand the basic physics behind the generation of the solar wind, that hot plasma has a pressure, and it makes the solar wind accelerate into interplanetary space. But the models that we have cannot explain the high speeds that we see. So we've known for a long time that there has to be an additional energy source to try and accelerate the wind. And indeed, that's one of the key science objectives of Parker Solar Probe, is to explain the flow of energy from the sun that heats the solar corona and accelerates the solar wind. So those theories that we've had so far have essentially fallen into two classes. One is that it's a process of intermittent release of magnetic energy on the sun. So the sun's magnetic field is very tangled, and the energy can be released in an explosive way, for example, in a solar flare. And so the theory is that there may be many more very small events on the sun, so-called nanoflares, which may be providing this energy source. The other class of theories is based on waves, that there may be a population of waves in the solar corona, and the momentum of those waves as they travel up away from the sun can actually accelerate the wind. And in fact, when we measure the solar wind near the Earth in these high-speed streams, we see an enormous population of waves filling interplanetary space in those streams. And so for a long time, people there's been a general view that probably waves is the answer to this acceleration problem, although we don't know the details. But now with Parker Solar Probe, we've gone closer than ever before, as Nikki has said, and that's revealed a radically different picture. So Parker Solar Probe at its first encounter, and this actually shows a picture of the sun during the first encounter, Parker was not connected to the large dark coronal hole on the left-hand side, rather it was connected to a small one on the right-hand side. And these white lines are model magnetic field lines emanating from that coronal hole towards the spacecraft, which was on the right-hand side. So as Parker flew through this coronal hole flow, it saw something really different to what we've seen before. And that wave field resolves into an enormous array, thousands and thousands of very fine-scale structures. These things are very short on the spacecraft timescale, from seconds to just a few minutes. And using Parker's unique orbit, we can use the information and the measurements that we make to actually understand the structure of these objects, and they turn out to be very long, thin tubes along the plasma flow. So they are hundreds of thousands of kilometers long, but their cross-section is incredibly small. So on average, these things are just a few thousand kilometers across, so about the scale size of the Earth. So for the solar wind, that's really small. So what are these structures that we see? Well, they have kinks in the magnetic field inside them, which we've shown schematically here. So let me show you a movie which sort of shows that in a bit more detail. So these are kinks in the magnetic field, and in fact, the magnetic field can be twisted all the way back as we go through these structures. And the magnetic field has a tension, and if you twist the magnetic field like this, it carries a lot of energy. So these things are carrying a lot of energy out into the solar wind, and actually as a result, they accelerate the plasma that's within it to a higher speed than the background solar wind. So the plasma inside these structures can actually have roughly twice the kinetic energy of the background solar wind. So that's an enormous amount of energy to feed into the solar wind, and clearly this is a key part of the puzzle as to how the sun accelerates the solar wind to such high energies. So we're seeing enormous numbers of these structures. So the wave field, therefore, that we see further out, as we go closer in, it turns out that wave field originally, when it's born, is actually a lot of fine-scale structure which evolves into those waves. So that means, therefore, the idea that maybe all of this energy is provided by waves is probably not the case, and rather there must be some impulsive process happening on the sun generating all of these fine-scale jet-like structures. So this is a movie of the sun taken roughly when Parker went through that first encounter. And what I hope you can see here, as well as the large-scale structure, is a lot of little dots and flashes going off all the time. This is plasma being heated by the release of magnetic energy. There aren't enough of these flashes, and actually they're too large, to explain what we see. But we think, therefore, there's probably a population of very small magnetic events happening across the sun all the time, and these are providing the additional energy source to power the solar wind. So this is early days. We don't understand the details of this yet. For example, we don't have an idea about the full magnetic field structure inside these objects. And clearly, we are not yet observing those events on the sun which explain what we see. So Parker, so far, has only gone to 35 solar radii, but over the next few years, as the perihelion drops down finally to under 10 solar radii, we're going to see these structures even closer to the sun than ever before. And I think rather than having sketches like this, in a few years' time, we're finally going to have the answer to one of the key questions from Parker Solar Probe, which is how the sun generates the solar wind and heats the solar corona. Okay, thanks very much. I'll hand you over now to Kelly, who's going to talk to you about something really different, some really large-scale structures in the solar wind.
Thank you, Tim. Hi, my name is Kelly Cork. I'm an astrophysicist at the Smithsonian, and I'm head of the science operations for the SWEEP instrument suite aboard Parker Solar Probe. So shown here, we see this coronal mass ejection, this very large scale. We have that similar EUV image of the sun on the bottom, and you see a flare happen, and this ejects tons and tons of mass out into the heliosphere, equivalent to 80 million school buses being thrown at millions of miles an hour out towards the Earth and towards the moon or any other place in the solar system. And so this is what view that we've had so far. We've done a lot of remote sensing. We do sense them in situ at L1, but we also at the near the Earth, but we also mainly view them in remote sensing. Now, Parker Solar Probe, we predicted that we would go in situ, probably fly through only one of them. And so we were looking at the sun during the first encounter. This is an EUV image of the sun from the stereo spacecraft during the first encounter. And you don't really see anything, right? You don't see those huge explosions that you did at first. Even if I kind of show you that, oh, you should possibly look here, there's no hints of anything actually going on in the extreme ultraviolet on the sun at that point in time. And this speaks to the fact that there's a class of CMEs called stealth CMEs that we don't quite know about and can't see in the traditional EUV. But if you do processing of these images from the stereo spacecraft, you begin to start to see that there are things flowing out of the sun and a coronal mass ejection coming out there to actually fly what Parker actually flies through. So we couldn't have seen this from the Earth because the sun was in between the Earth and Parker. And so we needed the stereo spacecraft in order to observe this. And why this is important, this here is showing a animation of a coronal mass ejection, those 80 billion school buses coming at us at millions of miles an hour, coming towards the Earth and actually interacting with our magnetic field, like Nikki said earlier. And what it causes is it can cause beautiful aurora, and that's one of the best effects of this. However, in our technologically driven society, it can also do things like wipe out power grids, interfere with satellites, and other things like as such. So we really need to understand how to predict these. And if there are things like a stealth CME, we're going to need to understand what those are, what that class of CME is. And Parker helps us by actually going there and actually measuring and seeing what the environment is and seeing how we can better detect those CMEs. So this is a plot I understand that only a scientist can love. It's not the pretty pictures, but this is the data that is so important to understanding those structures and what they're doing. The CME that you saw in the stereo images and the black and white images are here. This is the coronal mass ejection area that we're talking about. On the top, you have the magnetic field measurements made by the Fields instrument suite on Parker. The total magnetic field is on top. The blue are different components or different directionalities of the magnetic fields, and that characteristic twist is something we look for when we're looking for coronal mass ejections. We also have then the radial velocity here. We have a drop in density in this area, as well as a drop in temperature during that coronal mass ejection. So these types of studies are really going to help us understand what are the characteristics of these stealth CMEs so we can predict them in the future, especially to protect ourselves for things such as the energetic particles also associated with these things that can cause hazards to astronauts as well as to our power grids. So next up, I'm going to hand over to Nathan Schwagen to talk more about those energetic particles.
Okay, great. Thank you very much, Kelly. I'm Nathan Schwadron. I'm the head of the ESIS instrument suite, the Energetic Particle Instrument Suite on Parker Solar Probe. I'm head of the Science Operations Center and a professor at the University of New Hampshire. Today, I'm going to talk to you about energetic particles. Energetic particles move at the speed of light, and they're extremely hazardous both to humans in space and to electronic equipment in space. So we really need to understand the physics and use that physics to be able to predict and therefore mitigate the hazards associated with these energetic particles. I'm going to be telling to you today about our study with Parker Solar Probe by actually going there to the sun. We managed to discover one of the key missing links between how the sun produces flares and energetic particles from solar flares, and then how those particles end up at very, very high energies, ultimately to cause the hazards that they cause. And I'll be describing results from one of the largest solar energetic particle events that we've observed so far in the Parker mission. So to begin with, I just wanted to show a movie. This is a historic event, one of the larger events that we observed in 2002. And as this movie goes in, we're focusing close into a region of very strong magnetic fields near an active region, and you're starting to see reconnection and the flaring processes associated with that. Those release energetic particles. And in just a second, we're going to blow out, and you'll see the release of a coronal mass ejection that comes out through interplanetary space. And last, you see what looks like snow in the detector. Those are these energetic particles moving close to the speed of light that are actually penetrating the detector, and you're seeing literally the damage that's caused by these energetic particles. Okay, in terms of the hazards, there's an array of hazards associated with energetic particles. For astronauts in space, you have long-term problems such as cancer. There's also shorter-term problems in terms of skin issues, like serious burns, issues with the central nervous system and the eyes, issues associated with blood-forming organs, and at very high fluxes, these events can cause lethality. Relatedly, these energetic particles can also damage electronic equipment and lead to satellite loss. You're okay here. You guys don't need to run for cover. We're protected on Earth by Earth's atmosphere. Okay, so in this study, we are going to be studying as I said, the source of these events by actually going there close to the sun. And though the event that we observed was small compared to historically large events, we still are getting insight into the fundamental processes that are happening very close to the sun. This is a simulation of a larger historical event that was done by those guys right down there at the University of New Hampshire in predictive science. And it shows the magnetic reconnection, the changing the magnetic fields in the inner heliosphere, and on the far right, the release of energetic particles that are accelerated by the coronal mass ejection. So these processes are all fundamentally related. Okay, so now what we've seen on Parker Solar Probe, if you watch this movie, Parker Solar Probe is coming out of its second orbit. It's moving out to roughly half an AU. And at this point in the movie, you're going to start to see the release of a number of coronal mass ejections that actually pass over the Parker Solar Probe spacecraft. So here's one of those, and you can see that sweeps over the spacecraft, sort of on the flank of the coronal mass ejection. You can also see, in particular over here, if you watch this movie closely, what looks like material that's building up near the front of that coronal mass ejection. These coronal mass ejections are like snow plows, and they sweep up the material in front of them. And it turns out for the first time we've seen that sweeping process, how those coronal mass ejections also sweep up energetic particles from flares. And so it is those flares that end up at very high energies. And it's that process, it's observing that directly, that gives us key insight into how coronal mass ejections build up the dangerous fluxes of energetic particles we see. That is the missing link that we've discovered in this process. Okay, so at this point, I'm going to turn it over to Carl, who's going to tell you about dust in the inner heliosphere.
Thanks, Nathan. Good morning, everybody. I'm Carl Battens from the Naval Research Lab. I'm part of the Whisper Science team. And I'm going to switch things up a little bit for this final talk. You've been hearing pretty much all week, really, that Parker has returned some fantastic science results And it's already, just with a limited data return, is answering so many questions that we had going into the mission. And that's a sign of a great mission when right off the bat you're getting answers to all of these questions that you had. But one of the truly remarkable things about the Parker mission is that it's also giving us answers to questions that we weren't even asking. And in fact, what I'm going to talk about is a question that isn't even related to heliophysics. So the movie that I'm showing right here is data from our WHISPER camera during the first Parker Solar Probe encounter. So with WHISPER, we have the sun is just outside of our field of view. We're looking at basically looking at space in visible light. We keep the sun outside of the field of view so it doesn't blind our cameras. So we kind of block out the bright light. That allows us to see all the faint structures, some of the stuff you've been hearing about this morning. So you've got coronal mass ejections, solar outflow. That's all the stuff that the mission was designed to see, and we're seeing it fantastically well in this data. But what we're also seeing is stuff that's kind of familiar to us from our previous missions like SOHO and Stereo. We get these beautiful views of the solar system. So we get in the Milky Way going across the frame there. There's a beautiful star field in the background. There's planets in there. We see asteroids. So all of this stuff is, again, it's familiar to us. It's wonderful to see. But what's truly remarkable about Parker is it's showing us something, we've seen something in the data that we have never seen before on any of our instruments, and in fact, no one has ever seen before. So right here, this is very faint, but between these red arrows, there is like a very faint dusty line, and in a moment I'll play a movie and maybe you'll see it a little bit better. But that line is actually a dust trail, or maybe I should even call it a rubble trail. It doesn't look very big in this image. It's actually about 100,000 kilometers wide. It's the part of it that you see there is about 20-some million kilometers long. It's a huge trail, and it's a trail that's following the orbit of an asteroid called Phaethon. Now, Phaethon's kind of an interesting asteroid. It's a fairly big guy. It's pushing 6 kilometers in size. It gets very close to the sun, actually as close to the sun as Parker Solar Probe does. It also gets very close to Earth and is actually listed as a potentially hazardous asteroid, although there's no immediate threat to Earth. But what's kind of cool about Phaethon is that a couple of thousand years ago, it went by the sun and something happened to it. We don't know what, but something happened to it, and it released a huge, huge debris trail that we now call the Geminid meteor shower at Earth. So every year, our planet goes plunging through the giant meteor trail in space, and our sky gets lit up by all these shooting stars. And by coincidence, actually, the peak of the Geminid meteor shower is just this weekend. And what we're seeing in the WHISPER images is actually that meteor shower. Or it's part, I should say, it is part of that meteor shower. So I'm going to play this movie now. It's the same movie you saw before, but we've processed it slightly differently. And so you've got to use a little bit of imagination to see the trail, because it does kind of move through our field of view as we move around the sun. But trust me, it's there. So my colleagues at Naval Research Lab and University of Maryland, we've been studying this dust trail for a while, and we had several questions about it that we wanted to answer. The first thing we wanted to know was, like, what is the nature of this trail? Where did it come from? So I mentioned that Phaethon gets very close to the sun. It gets as close to the sun as Parker does. When it gets close to the sun, that solar radiation heats up the surface and actually causes the surface to fracture, and it releases dust. So we know when Phaethon goes close to the sun, it's releasing dust all of the time. And so our first question was, well, is this dust something that is being released by Phaethon now every time it goes by the sun, or is it something related to these Geminids that happened a couple of thousand years ago? And so we have calculated the mass, so how much stuff basically is in this whole trail, and it's something on the order of like a billion kilograms. It's a billion kilograms, or 1 million tons of material. And we know that the rate at which Phaethon produces dust near the sun is nowhere near sufficient to create the massive dust that we're seeing in this trail. However, we also know that based on the rate at which meteors come into our atmosphere every December, we know that the amount of dust we're seeing here is more comparable to the amount of dust that's contained in the Geminid meteor shower. So we're very confident that we are indeed seeing the Geminid meteor shower. So that's really one of our sort of main conclusions from this. The importance of this is that people have been looking for this trail for a long time. We know it exists because our planet goes plunging through it every year, but we don't really know the structure of the trail. Like, is Earth flying through the most dense part? Are there other parts of the shower that are more dense than others? And so just even a couple of years ago, there was a Hubble telescope search for the trail, and they were unable to detect the trail. In our study that we've done here, we have actually figured out why Hubble was unable to detect it. I'm not going to get into that right now. I'm happy to answer that question. But we are, with this data and in successive passages by the sun, because Parker's going to go by the sun a whole bunch of times, every time we go by, we're going to see this same trail, we're going to get these same observations, and every time we're going to learn a little bit more about this trail and really start to address some of the questions that we have about this meteor shower that we pass through every year. So with that, I know all of us are really eager to talk about our science and answer your questions. So I will open the floor to questions, and thank you all for your attention.
Be shy.
Yes. Yeah, Phaethon, yeah.
Phaethon goes by, does it go on the same path every year, or does it change?
Yes, Phaethon is on its own. It's on a fairly stable orbit on reasonable timescales. It's on a pretty stable orbit. And Phaethon is on a very slightly different orbit to the Geminid meteor shower. So although Earth passes through the Geminid meteor shower every year, thankfully we don't cross paths with Phaethon every year, because that would be quite scary. Yes, dinosaur scary, yes.
Sorry, do we have more questions from reporters?
Hi, I have a question about the stealth CMEs. What is the significance of them? Are they different from any other CME in any other way besides how we can see them?
In general, they tend to be smaller, but it really is that lack of detection. And so detection is what we really need to do in order to save ourselves from space weather. So that's the major difference, is just not being able to see them in the extreme ultraviolet.
Sarah? I also have a question about the stealth CMEs. So the reason that we're not seeing them in ultraviolet is that, does that have something to do with, like, I guess, what do we think is making them so stealthy? And then how are we going to get around the fact that we can't see them through traditional methods? And then I also have a clarification for Nathan after that question.
Great. Yes, so how we're going to get around it is measure it in situ and measure these as they're coming off. And as you saw in the processing, we were able to process the data in different ways to try to bring it out in the visual. And then in situ, it's easier to actually measure the changes in magnetic field and tell that that's it. But that's also part of Parker's mission, and what the data is starting to reveal is that the magnetic just topology in general that happens near the sun is different. And so we're going to need to do a lot of detective work and have a lot more data from Parker to see the switchbacks and the stealth CMEs and how they all kind of relate to each other in that magnetic family of structures around the sun.
And does the sort of stealthy quality, does that indicate to you that maybe they're produced via a different mechanism than the sort of regular CME, or?
Exactly. It hints at where their source is and where that material is actually coming from in the corona, how high up, how low down type of thing, because we don't see them brightly in the extreme ultraviolet.
So what is the hint? What do we think is different about these ones? So the hints then are
the fact that you do see them in the, you can see them when they're processed, when the things are processed, so you're actually seeing the material come off And then there's been a lot of modeling. So some of the modeling, to go back to the source of where these CMEs come from, it was a connection between the polar coronal hole and something at basically the equator of the sun reconnecting and then shooting out that. So it's not as localized, in some ways it's not as localized as it was previously, as you see when you have a bright ejecta coming off.
And then, is it okay if I ask? Okay, so Nathan, I just wanted to clarify. So what your results indicate is that the thing that is causing these energetic particles to become so energetic is them getting pushed out by the snowplow of the coronal mass ejection, or?
It's actually we're observing a process that happens before the large amounts of energization that happens further on. So we've never been able to observe these processes happening so close to the sun. And as a result of that, we're able to address a question that we've had for years, and that is how populations of particles build up prior to being accelerated. And so we were able to make the direct observation for the first time of the populations that are produced by solar flares building up in this snowplow region in front of CMEs. So that buildup of fluxes right now, we see it in very early stages before a lot of subsequent acceleration has happened. But we still now understand that buildup. We can start to understand the buildup process, which then preconditions the acceleration to much higher energies.
It's like when you get those big drifts on the side of the road.
Mm-hmm.
Snowplows that accumulate.
Exactly, yeah. Yeah, we've never seen this material in the process of building up in those regions. And so it's always been a question as to where that came from. How did that buildup occur?
Hi, I'm Catherine Cornai, freelance writer. Question for Carl. In the images you showed, there were other trails. Are those other asteroids? What are those?
No, a lot of the trails you'll see in those images are dust streaks just from sporadic pieces of dust in space, not related to the trail we're seeing. It's just that the region of space we're flying through is relatively dusty, and we're kind of bombing through at 80 kilometers per second. So we're seeing quite a bit of dust in the images.
So how did you pinpoint it to this asteroid? Do you know the tracks of all of them and you just correlated, or?
Yeah, I mean, it was kind of a case of, okay, we see a big trail, it looks like a dust trail following something. What do we know that goes in that region of space? And so we start kind of testing a few things, and then you plug in the numbers for the orbit of the asteroid Phaethon. It's like, oh, hey, look at that. It's a perfect match. So that's how we figured that one out.
Daniel Stolte, University of Arizona. I'm also curious about Phaethon. So that trail that you saw, am I assuming correctly? It's you said it's about 200 million kilometers long, something like that. So it's not circular, right? Is it just where it gets closest?
I'm glad you asked that, actually, because I wanted to clarify that point. We see a portion in the images. We are seeing a segment, roughly like a 20 million kilometer long segment of something that is a complete orbit in space. So the whole thing, I think, is like 6 astronomical units long or something like that. So, but I was just pointing out that we're seeing some portion of that passing through our images.
Cool.
Are you a reporter? Are you a reporter? No.
I'm sorry.
Okay.
Do we have further questions from reporters in the audience? Chat, Sarah? No questions on chat? Going once, going twice. All right, I'm going to close this then. Thank you to our panelists. I'm sure they'll be here for a few minutes if you come up with some more questions. We're going to resume at 11 with an update from ESA's solar mission. You want a double header?
side. Well, you're tall enough to come this side. Yeah. Okay. Wonderful. The light doesn't actually matter. Oh, okay. I know, yeah, it seems weird, but he's gonna control the flash. Okay. Yeah, so don't worry, yep, nope, you're good. That's it. All right, we'll give him like 1 or 2 more minutes. They're still. Awesome. You have a clicker here, pointer, pointer, flat clicker, yeah. All right.
Does the mouse configure as well?
I don't know because he's running it back there.
Ah,
Because it's the keynote. Yeah, yeah, yeah.
I think arrows always have this thing of
The arrows, we can advance the slides with the arrows, down arrow.
I think he's controlling it because he's running it's a keynote presentation. Yeah. Hold on. Let's see. Hey, Scott, you're going to advance the slides, right? Or from back there? We can do it up here with the clicker? Okay. Great. Okay. Mouse or clicker?
Yeah.
All right. Wonderful. Okay, we're going to go ahead and get started. All right, this is our 11 a.m. press workshop. This is Get Ready to Face the Sun with Solar Orbiter. So our participants today are Holly Gilbert from NASA's Goddard Space Flight Center, Daniel Mueller from the European Space Agency, and Marco Velli from the University of California, Los Angeles.
Good morning. My name is Daniel Müller. I'm the project scientist for the European Space Agency, and together with Holly Gilbert from NASA and Marco Velli from UCLA, we'll be talking to you today about the Solar Orbiter mission, which is a mission of joint collaboration between ESA and NASA that will study the sun and the inner heliosphere. And it's going to carry a comprehensive suite of 10 instruments into the inner heliosphere. And it will measure all the way from the solar surface into the solar wind. And this collaboration is building on the successful joint projects between ESA and NASA in heliophysics, like the Ulysses mission, which lasted for 20 years until 2009, and the SOHO mission that was launched in 1995 and is still going strong. And the overarching science question that Solar Orbiter will address is about the magnetized plasma bubble that the sun blows into space that we call the heliosphere, and why solar activity changes in time. And you can see an artist's rendering here of the bubble around the sun, the heliosphere, and in small spacecraft, these are the Voyager spacecraft that took 40 years to travel through the heliosphere, measuring the plasma as they went along. And we're going to join them and explore the inner heliosphere in more detail. And if there's anyone who is not getting excited about the plasma around the sun, even for astronomers, this is interesting because astronomers can sometimes see the astrospheres of other stars, because most stars have these spheres of gas surrounding them. But in the best case, you can use a big space telescope like Hubble to see the bow shock, but you cannot really measure the details. For doing so, you really need to fly there and measure at the location of the spacecraft and sample the plasma. So just in a nutshell, the sun, as you will most likely know, is a fusion reactor that fuses hydrogen into helium. And because of this famous formula of Einstein that relates energy to mass, this tells you with the speed of light squared that you just need a little mass that you convert into energy. And with this large number, you get a lot of E for just a little m. And the sun has this fusion reactor in the middle, and it just transports the energy outward, and this magnetic field is what really matters. And as soon as we go outwards from the sun, it's all about magnetic field. So inside the sun, we have moving charges, and they generate magnetic field. And the so-called dynamo in the inner part of the sun at the base of the convective bubbling envelope generates a magnetic field, and these bundles of intense magnetic field then rise up because the magnetic field expels partially the plasma. So these are really like straws or spaghetti of magnetic flux that rise up through the surface of the sun, and they penetrate the surface and they make dark spots that we know as sunspots. And they are dark because the magnetic field channels the motion of particles, pretty much like a highway channels the motion of cars. And this is why they appear dark, because they are cooler. And ever since people set eye on sunspots about 400 years ago with the first telescopes, they have been counting and essentially keeping track of sunspots numbers over time without fully understanding what they actually were until roughly 100 years ago, when Hale was measuring the line splitting of a spectral line in a sunspot and could really pinpoint that this is due to magnetic field. So the sunspots follow a periodicity of 11 years, plus minus 1 or 2 years, and you can see a clear change in solar activity along with the number of sunspots. You can also measure in space, with the blue line, the total magnetic flux in the heliosphere over time. So what you see is a relatively good correlation between the surface magnetic field of the sun and what's happening in the plasma bubble around it. But it's not perfect. There are things that happen between the sun and us, and we simply don't understand, and the only way to find out is going there, like Solar Probe has started doing last year, and that we will start doing in just 2 months' time. So we'll hand over to Holly now.
I have to lower this. Great, thanks. So as Daniel mentioned, the sun is magnetically driven. It's very dynamic. Those magnetic fields provide a wide range of solar activity, and that solar activity can impact us here in the near space environment in the Earth, but also planetary atmospheres throughout the entire sun's domain. And we call this impact space weather, which is really a chain of complex processes, physical processes extending from the sun to the Earth. And space weather is something that you heard about in the previous press conference as well. It can ignite the aurora, which is perhaps the most well-known space weather phenomena. In fact, there is a Northern Lights tourism industry in some of the Northern European countries. And as beautiful as they are, there are hazardous aspects to space weather as well. The very same charged particles that come and interact with the Earth's magnetic field as they're blown away in these big coronal mass ejections, they interact with the Earth through a series of processes. The charged particles get accelerated at really high speeds, interact with the atmosphere, and create these beautiful lights. But again, there are hazardous aspects to space weather. They can impact orbiting satellites or spacecraft, GPS signals, communications, power grids, even polar flights that are more susceptible to that extra radiation in the poles. And NASA is very interested also in the impact in astronauts. So this is very important for human space exploration, especially as we're sending people back to the moon and to Mars, where they're far away from the magnetic shield, the magnetosphere of the Earth and the atmosphere. Solar Orbiter will help address some of the fundamental science questions behind space weather and behind that activity. It will launch in February. The window opens February 5th. It will launch on a launch vehicle provided by NASA, an Atlas V, and the cruise phase is 1.8 years, and the nominal mission is 4 years with an extended mission of 3.5 years, and hopefully more than that. The orbit is of particular interest and very unique. It's an elliptical orbit, but what's really, really unique about it is that it gets out of the ecliptic, which is not easy to do, and Daniel will explain a little bit of that later. But we need to get out of the ecliptic if we're going to look at the poles of the sun. We've never been able to image the poles of the sun. That is extremely important for helioseismology, but also for looking at the global magnetic field of the sun. In order to model space weather activity and activity in general on the sun, we need that full global picture of the magnetic field. So orbiter will be out of the ecliptic, allowing us to see the polar regions for the first time. It's actually really exciting. And also, it will have a reduced relative rotation. So as it's getting close to the sun, it will be rotating at close to the same speed, and so it will allow longer observations of those regions on the sun. Now, we have a combined suite of instruments, remote sensing and in situ, which is incredibly important when we're trying to figure out and address some of these fundamental questions. The remote sensing observations, the windows, of course, are going to be taken when we're closest to the sun, but also, as I mentioned, the high latitude observations. So each time that we're out of the ecliptic and as we get pumped up, the remote sensing instruments will be taking data. These are very ambitious science objectives. We hope to address and help further our understanding in a lot of these, but again, it requires a lot of different data. This is an incredibly powerful combination of in situ and remote sensing, and we need all of these measurements, again, to help address some of these major outstanding heliophysics questions. So we're going to have measurements of the wind, the solar wind plasma, the fields, the waves, energetic particles. And I should mention the other reason for getting out of the ecliptic that is important looking at the poles is that's where the fast solar wind comes from. So we're going to be able to look at it and measure it from the polar regions. At the same time, we're going to be able to image the observations and in and out of the ecliptic plane, and also get a handle on the magnetic field of the solar photosphere, which is the bottom layer of the solar atmosphere. I can't really emphasize enough the importance of the combination of the remote sensing and in situ. It will allow a connection. It will allow us to look at the source regions on the sun where things are happening, where the activity is happening, and then measure that plasma that we're seeing ejected or coming out and measure it at the spacecraft. So there's an incredible, great thing about connecting that plasma, which we haven't really been able to do except at the Earth, which is a lot further away than we would hope. So we're very excited. I'm going to let Daniel talk more about the orbit and the spacecraft.
All right. Thank you, Holly. So like Parker Solar Probe, we'll be using Venus and also Earth to slingshot in different ways closer to the sun and also out of the ecliptic plane. And we've condensed the 10-year journey into half a minute, so it's fast, but it'll loop in case you miss any key features. So we'll launch in February. We'll already, after about 4 months' time, have an approach of about half the distance between sun and Earth, half an astronomical unit. And we'll have 3 gravity assists, where effectively we use the planets, Venus and Earth, to break down the spacecraft, give them some of our momentum, and to let them fall into the sun. That's the whole name of this almost like a billiard-like game, that you try to lose angular momentum to then approach the sun closer and eventually nudge your orbit so that you slingshot out of the plane of the other planets to see the polar regions of the sun for the first time. So what you see here are, the orbits of Mercury, Venus, and Earth. And as we move along, we'll get into a resonance with Venus that takes 225 days to revolve around the sun once, and we'll get into an orbit where we hit Venus every couple of orbits and use that to gradually increase the ecliptic, the orbit out of the ecliptic plane. So this is a rendering of our spacecraft. Like Parker Solar Probe, it's dominated by a massive heat shield because we get close to the sun. We get up to 13 times the heat flux of what a satellite would see at close to Earth. The design of the heat shield is such that we have 2 panels of carbon fiber. They are wrapped into thin titanium foils with a particular surface treatment to make it extremely robust against energetic particles and degradation over time. It's black, and the idea is that once it's pitch black, it can't get any blacker. Over time, it will just remain as is, and it has a gap of about 10 inches where energy will be radiated outwards to keep the temperatures down at the backside of the heat shield to roughly 50 degrees centigrade. So I would say that's maybe about 120 degrees Fahrenheit, give or take, and about 500 degrees centigrade on the front side, which is roughly 1,000 Fahrenheit. So it's more than a pizza oven on the front side, and on the back side it's a toasty day in Arizona probably. The one thing which really is remarkably different compared to Parker Solar Probe is that we will be able to look at the sun. This is impossible if you go as close as Parker Solar Probe, but we are staying out just at the distance where we can still build imaging telescopes and protective layers in the optics to make them work. So they are peeking through the heat shield. We have little doors to slide open to let them look through. And we'll tilt the solar arrays as a function of distance to the sun to make sure that they won't melt in the sunlight. We'll almost have them edge on when we are at the closest approach. So we have instruments that measure the solar wind at the location of the spacecraft. It's like sticking your finger into the solar wind, or the Latin term is measuring in situ. We measure the energetic particles. We measure the magnetic field. These sensors are mounted on a long boom to keep them outside of the irritating noises, electromagnetic noises that the spacecraft makes when moving certain mechanisms. These sensors want to be undisturbed and really in the solar wind, ideally not see a spacecraft at all. This is why we put them on a long boom. It's the electron sensor of the solar wind analyzer at the tip of the boom, and the radio and plasma waves antenna are long, 6.5 meter elements sticking out. And here we have the telescopes that are hidden behind the heat shield. They take images and spectra in the visible, in the UV, and in the X-rays. And in addition, we have a wide field imager that makes some of these movies like you've seen from WISPR on Parker Solar Probe, where you look away from the sun and image a wide region of space. Now back to Holly.
So as you can see, this is truly an international collaboration. We have 10 instruments, and each instrument has a principal investigator, some of whom are here, including Tim, who you saw at the previous conference. But you can imagine that it takes a lot of coordination. It took a lot of coordination to get all these instruments integrated onto the spacecraft, and it will continue to take a lot of coordination for science operations and to really get the best science out of the combination of all these instruments. That's an image or a picture of the spacecraft in Munich right before it shipped after all the testing was done. And so here are some beautiful photos. It's really gonna happen. These photos make it become even more real. And so the spacecraft had to get flown to the Cape Canaveral, where it's gonna launch in February. And you can see photos of that here. And also, the rocket that NASA's providing, it's had to be shipped on actually the ship called Rocket Ship. And so those are the images over there. So it's really coming together. And NASA is extremely excited. We are not only providing the launch vehicle, but also 2 of the instruments. And this is going to be an amazing augmentation to what we call the Heliophysics System Observatory, our fleet of already existing spacecraft and missions. And so of particular interest is one that you've just heard about, Parker Solar Probe. There's a great synergy between these 2 missions, and we're very excited about it. And I'll let Marco explain some of that.
Hi, so you've seen a press conference just now about Parker Solar Probe. That is a mission that's going in situ really close to the sun to measure the plasma and magnetic fields. And so you might be startled and ask, why solar orbiter? Why is this? So there's a few reasons why it's very important. And let me first say a few things. One is that the sun produces, the energy that we all use on the Earth. It provides life for us here. And it really only a few thousandths of a few percent of its energy goes into the magnetic field. So why are we so worried about this? Well, you've seen space weather. But the property of magnetic fields is that they focus energy and they release it in really small regions of space. And therefore, they can bring intense, huge amounts of energy. Coronal heating, for example, produces the same amount of energy as a few hundred million hydrogen weapons exploded every hour in the atmosphere of the sun. Now, To explore what's really happening from the surface of the sun outward into space, you also have to realize that the gas that is almost invisible. Yes, we've seen these beautiful images of the corona, but it's like looking at a cloud. And a cloud has no physical surface. So Parker Solar Probe has an imager, and it is inside that cloud and is looking at it. And Orbiter is much further away, and it has a different set of instruments and complementary set of instruments. In particular, I will focus on just a couple. One of these instruments, for example, is a composition measurement. Composition doesn't change. Once the sun has emitted particles, that composition can no longer change. And so the spectrum of elements that are there are like canaries in a mine. They tell you some specific information about what kind of particles are coming, and therefore they can identify the location on the sun where they're coming from. And of course, that produces an immense potential synergy between these two missions. As you've seen, Solar Orbiter will spend time in the ecliptic plane. So as you can imagine, there will be many, many times when Orbiter and Parker will be measuring essentially the same plasma at different distances from the sun. And the fact that Orbiter can also measure composition will allow us to determine where on the sun the events happened that created the solar wind that we will be seeing. The telescopes, we've mentioned there's 5 or 6, depending on how you count them, telescopes on Solar Orbiter, and these allow us to see the corona all the way into the atmosphere of the sun. Parker Solar Probe will be going in and out, and now I'll show you essentially what kind of potentials there are. So one we've already mentioned, which is essentially the alignments in the gas. So the solar wind is emitted, and Parker and Probe can see either there are phases of the orbits where Orbiter is further from Parker. It can also be the other way around. And this will allow us to trace the history of the plasma from the sun as it travels outward and to understand the basic physical phenomena that are going on. In addition, sorry, what did I just do there? In addition, the magnetic connection is fundamental as well. When energetic particles are emitted, they tend to travel along the magnetic field. And this is a different way of illustrating kind of the same thing. So when a bursty event happens, we can trace it all the way from the sun to the Earth, basically live. And finally, of course, there's the other fundamental property, which is that there are some imagers also on Parker Probe. Parker Probe takes beautiful images of the solar corona. There are similar instruments on Orbiter. In fact, one called a heliospheric imager, which is essentially of the same type and built by the same team at NRL. But there are other coronagraphs and other remote sensing instruments on Solar Orbiter. And now you can imagine that you are seeing these clouds, because it's a transparent thing, and we can't really measure the details of them, but seeing them from multiple points of view at the same time will give us much more information than seeing them from one point alone. A final point is the fact that measuring in situ, as Daniel explained, is fundamental. Measuring from far away is fundamental. And the reason is the magnetic field is so important in focusing and determining the properties of particles, and we cannot see the magnetic field from far away. So the point of it is we see the magnetic field on the sun, probe measured in situ. Orbiter can connect that magnetic field that we see to what is seen in situ. And so we're really facing a decade, I think, with these two missions, and of course the new ground-based instrumentation, the high-resolution solar telescopes that are about to be operated by the NSF and a little bit further in time in Europe, that we will really unravel solar magnetism in itself. And as Daniel also pointed out, I would like to make sure you understand that magnetism is fundamental to all of astrophysics and the universe itself. The phenomena that we see, we had no idea when the first spacecraft went out in the 50s and measured what was going on in space. We had no idea that these were the basic fundamental phenomena that were occurring everywhere else in the universe, from the corona of galaxies to the corona of other stars with different types of energies, things called collisionless shocks, which sound like a contradictory term in itself, but that are happening thanks to the complex interaction of plasma and particles. And therefore, I think we can safely say that with the accomplishment of these two missions, our understanding of what's called the basic astrophysical plasmas of the solar system and the universe will have changed entirely. And I think with this, we can go to questions.
All right, so now I'll open it up to questions from reporters in the room. Just remember to state your name and affiliation.
Harvey Lyford, freelance writer. I just have a question about the launch date. Is it critical in view of where the planets are at that time, or are you flexible about when it might launch in case of weather or whatever?
It is critical because this is more like a planetary mission in that we need to use Venus to get gravity assist. But our window of the launch window is about 3 weeks. So we have 3 weeks to capture that particular orbit. And but yes, it's not as flexible as other missions.
Do we have other questions in the room? Think about it for a minute. Do we have any questions on the chat? No? Any other questions? Going once? Going twice? All right, we'll conclude there. Thanks, and thank you so much to our panel. And if you guys want to stick around for a little bit in case anyone has individual questions. And we're going to reconvene again at noon in a half hour for microplastics in unexpected places. And then our afternoon schedule is going to be clear for the Bloomberg talk. Thanks. Yeah, so just to clarify, microplastics is moving up to noon. Definitely stick around for it. And then their whole afternoon is clear. All right, we'll go ahead and get started then. Everyone, thank you so much. This is our 12 o'clock panel. This is Microplastics in Unexpected Places. And we have a panel of all undergraduate researchers presenting today. So very exciting. I think that's a first for an AGU press conference. So our panelists today are Julia Davidson from the Desert Research Institute, Emmeline Raghunath de Matos from Columbia University, and Meredith Sutton from the University of Virginia. And we actually have a physical sample that Emmeline brought in for her presentation of fabric samples. So if anyone would like to take a look at those or a feel of those, just come up to the front after the press conference is over.
Hi everyone, my name is Emmeline Raghunath de Matos and I am an undergraduate student at Columbia University. This summer I interned at the Lamont Dorothy Earth Observatory where I worked with my partner Mariella Carrera, Senior Research Assistant Kaylee McKee, Dr. Helga Gomes, and Principal Investigator Joaquin Goes. What we worked on this summer was what is the role of microfibers from clothing in the aquatic environment and their impact on zooplankton. Now, before we get into microfibers, I just want to let you all know a little bit about microplastics. So what are microplastics? Microplastics are defined as plastics that are less than 5 millimeters. They are categorized as microbeads. These are spherical in shape, and they are generated from products such as facial cleansers and other pharmaceutical products. Another type would be microfragments. These are irregularly shaped, and they are generated from the photodegradation of larger plastics. So these are what the microfragments look like. And what I worked on this summer was the microfibers, and these are hair-like structures, and they are generated from our clothing. So each one of us contribute to the microfibers that are ending up in our oceans. Now, we know that microfibers are being shed through our clothing. But what we did not know was which type of fabric sheds the most amount of fibers. So our team and I, we set out to investigate this, and we partnered with Dana Cohen, who is a fashion designer. She was able to procure 33 different types of fabrics for us, and these different fabrics came from different countries such as Italy, China, Australia, and of course the US. And what we did, we wanted to launder these fabrics. Now, each fabric was treated similarly. They were both cut into 1 square foot by 1 square foot pieces, as well as they were hemmed. Now, next they were laundered both with and without detergents. Now, once they were laundered, the wash water was filtered, and we were able to determine the mass of fibers that were released within the wash waters. So, without the use of detergents, we saw that polyamide types of fabrics shed the largest amount of fibers, while polyethylene and nylon sheds least. So this is an image of the fibers that we collected from the wash waters. Now, once we used detergent, we saw that polyamides shed the largest amount of fibers, while recycled polyester shed the least. And this is another image of the amount of fibers that we collected from the wash water. Now, we categorized these 33 types of fabrics into 9 categories. They were hemp, polyethylene, biodegradable nylon, nylon, tensile, viscose, recycled polyester, and polyamides. Now, in this top graph here, the light orange shows the fiber loss, the average % of fiber loss without the use of detergent, and the dark orange shows the fiber losses with the use of detergents. Now, when you compare without detergent and with the use of detergent, we can see that the amount of shedding was almost 3 times with the use of detergent. Now, another part of our project, we wanted to determine the amount of lint that is trapped in the dryers, and we were able to determine these amounts. So the light green colors show without detergent, and the dark green color shows with detergent. And again, we can see that with detergent, there was more fibers that were being trapped in our dryers. Now, once we compare our washing process with our drying process, we can see that drying releases much more fibers compared to the washing. So just to give you a comparison, this here is our polyamides, and these are other fabrics that were tested. So polyamides here shed the most both with and without detergents. Now, we wanted to know what about these detergents caused all this shedding, and then we wondered, what if detergent formulas actually contained microplastics themselves? So we partnered with the students of Uncommon Charter High School, and they tested these different brands of detergents. So these brands of detergents can be categorized as organic brands and regular brands. Now, in order to detect microplastics on a microscopic level, they used a dye called Nile Red, and what that does is under ultraviolet light, it fluoresces. So the images I'm about to show you, anything that you see fluorescing is considered a microplastic. So in the organic brands, these that glow are microplastics. And in our regular brands, these were the microplastics that were found. So these are contributing to the amount of microplastics that enter in our ocean. Now, at Lamont Dorothy Earth Observatory, we partner and collaborate with other scientists and other students. One such student, Shelley Lim of Barnard College, conducted a study within New York waterways, and she wanted to quantify the amount of microbeads and microfibers within different areas of the New York region. So from areas 1 to 7, this is the Long Island Sound area, and 8 through 14 were other areas within New York. Now, what is important to note is that the larger the dot, the more the microbeads and the more the microfibers. Other research included surface water samples. So here is the Connecticut River. Surface water samples were taken here. And this is other areas within the Long Island Sound area. Surface water samples were taken there. And we were able to see that there are a lot of microplastics, both all of them having fragments, fibers, and beads. So you can see that we have a large amount of fragments in both areas. Now, another part of this project included the Calanus copepod species of zooplankton. Now, this is a very low trophic level species of zooplankton, and in this region of the Long Island Sound area, we collected these species, and what we saw these amount of fragments, fibers, and beads that were within the bodies of these tiny organisms. Now, remember, this is a very low trophic level, so it means that other fishes feed on them, so it tells us that there's the possibility for bioaccumulation of these plastics. So thank you very much, and I would like to acknowledge some of these professors who helped me. I would now pass you on to Meredith.
Hello, everyone. My name is Meredith Sutton. I'm an undergraduate student at the University of Virginia, and I've been working with Dr. Bartelt Hunt at the University of Nebraska, studying the occurrence and fate of microplastics in the agricultural environment. So this is primarily in response to the application of biosolids, which is an agricultural practice that I'll talk about more in just a bit. So, much like Emmeline's group, we're just trying to pinpoint a source of microplastics as they're entering the environment. And this is primarily because of their increasing prevalence in the environment and the possibility that they may have negative effects on different ecosystems and human health. So, when researching the distribution of microplastics over different types of environments, not only have we found indication of increased microplastic concentrations downstream of urban areas, so like cities, which was fairly expected. We also found indication of increased levels of microplastics downstream of agricultural areas. However, there's been little to no research on the type of agricultural practices that could be causing this increased level of microplastics. So our research group chose to study the land application of biosolids. And this is primarily because biosolids tend to have a high microplastic content. And so I'm going to give you guys just a quick kind of background on biosolids. Biosolids are a product of wastewater treatment plant sludge. So this sludge is the solid components that are left over after the wastewater treatment process. And then they can go through their own treatment process and then be land applied as fertilizers or soil amendments in agricultural areas. And so the issue with this is that when they go through this treatment process, it does nothing for the microplastics that the sludge have accumulated in the wastewater treatment plant, primarily due to the washing of fibers and things like that, as Emmeline discussed. So when they're applied to fields as biosolids, it's comparable to applying a concentrated source of microplastics directly back into the environment, which obviously is not good. So for this study, our main goals were to try to see if the application of biosolids resulted in an increased microplastic content in the runoff leaving these fields. And then we wanted to see if there was a certain size or shape of these microplastics that were more likely to end up in this runoff. And so the answer to both of these were yes. The land application of biosolids did result in higher concentrations of microplastics in its runoff, and there was a preferential shape that was transported, and I want to talk a little bit more about these in just a minute. So in order to get these results, we set up 4 test plots at Rogers Memorial Farm outside of Lincoln, Nebraska. And 2 of the plots were applied with biosolids to meet the nitrogen requirement for corn, which is a popular crop in the area. And then 2 of the plots were left as control plots, so no other soil amendments were added. They were just left alone. And so after significant rainfall events, we would collect samples and then analyze these samples using UV microscopes. And when these the UV light interacts with the plastics, it causes them to fluoresce a blue color, as you can see in this picture. And these are 3 out of the 4 microplastic shapes that we looked for. So these include films, fibers, and fragments. As Emily mentioned, the fibers and fragments, we were also looking for the microbeads as well, but they're not included in this picture. So, as I mentioned earlier, and our initial results were very positive, we did find that biosolids contributed an elevated concentration of microplastics into the runoff leaving these fields. And you can see this in these 2 bar charts that are for the 2 different types of runoff samples that we collected, both liquid and mixed samples. And so these charts show the microplastic concentration for each sampling date that we took after a rainfall. And the red bars denote the experimental plots. So runoff from these plots are the plots that have the biosolids applied. and then the blue denotes runoff from the control plots. And as you can see, for every sample during every sampling date for both the mixed and the liquid samples, the runoff from the plots with biosolids have a higher average concentration of microplastics when compared to those in the control plots. So this shows that there is an increased amount of microplastics leaving these plots. We also looked at the shape and size of microplastics and the runoff leaving these plots, and we found that the primary shapes leaving these plots are both fragments and fibers, with fragments having a much higher percentage than the fibers. And so this is going to help us categorize kind of the composition of the microplastics leaving these areas. Further, we also found that the fibers that we were looking at were all smaller than, primarily smaller than 2 millimeters in size. So this shows a more preferential treatment towards smaller microplastics. And if you think about that, that makes sense, because if the microplastic is smaller, then it's much easier, it takes less energy for it to be transported from its source. So in conclusion, we found that the land application of biosolids is an agricultural practice that contributes microplastic pollution to the agricultural environment, and then these microplastics can further be transported downstream and possibly end up in larger water sources like the ocean. And we also found that the microplastics transported from these areas are smaller fragments and fibers, and so this will help categorize the type of pollution, the microplastic pollution that's leaving these agricultural areas. And we definitely want to look further into the future and look at different agricultural practices to see where other microplastics are coming from in this environment. So I'll now pass it on to the next person.
Oh no. All right. Hi, my name is Julia Davidson. I'm an undergraduate student at the University of Nevada, Reno. So far, we've talked about how microplastics are entering the environment, but we haven't really talked about where they go after that. I've been working with the microplastics team at Desert Research Institute, and we were able to find microplastics in snow. And the snow that we looked at was remote areas, far away from any human contact. It was about at least 150 to 200 miles away from any human developments at all. And then on your left, you can see one blue fragment that we found within one of the snow samples in one of the pristine areas, like you can see on the right. So these environments, like the one up top, they look clean and they don't look very polluted, but when you zoom in really close, we end up seeing this contamination of different microplastic particles like the one shown on the screen. The blue, larger particle is a fragment, and then the red one is a microfiber, and then we see another green fragment below. And it matters that we're finding these contaminants in the snow, because the snow melt could be used for drinking water, which could be consumed by humans or animals, and we don't really know what health effects it would have if we were to be consuming these materials. Because these particles are plastic, they're going to be long-lasting, and they're not going to really exit the environment on their own. And for us to go in and to remove all of these microplastics would be very difficult, since they're so small and spread out so widely. So our process in this experimentation was we dug a snow pit and we collected snow from different layers within the snow pit. And then we filtered it through funnels into little filters, and we examined the particles on the filters with a stereo microscope. We imaged it and we magnified it, and then we examined the particles on the filters. You can see a fiber shown on the far right, and if you look at one of those squares are going to be about the size of a single piece of human hair, if that gives you an idea of how small these particles really are. We noticed a few things while looking at the data that we collected. The first one is that we noticed most of the particles were microfibers, like you can see below, and these could possibly be coming from clothing, as we discussed earlier. The second thing we found is that most of the microplastics were within the surface layer of the snow. We think that this may be because we think that the particles may be deposited onto the snow through the air, and the layer at top is going to have more time to have access to the air and have the deposition from the air as well as with the snow. As you can see in the graph, that top bar is the amount of plastics we found in the top layer, and then the layers below show the amounts we found in those ones respectively. So this is the second study ever to be done on the presence of microplastics within snow. The previous one examined microplastics within the Alps and the Arctic, and they also found a presence of microplastics in those remote locations as well. However, this study did not examine the different depths, so they weren't really sure of how the plastics were being deposited into these remote, faraway locations. And because of this, so as you can see, the different locations that all the studies examined were very far apart. So we don't really think that this presence of microplastics in remote areas is regional. We think that this problem is widespread. We think that these microplastics are able to travel these long distances into these faraway areas because they're so small, which allows them to be traveled, or it allows them to travel across the great distances easier. Our results so far are very preliminary. We still want to examine more study sites and improve our methods, but we can say for sure that we are finding microplastics in these remote areas where we're not directly depositing them, but they still end up there anyway. These microplastics could then continue to contaminate freshwater sources, such as Lake Tahoe. My colleague Zoe, she examined collected a sample at Lake Tahoe, and she examined the filters, and she was also able to find a presence of microplastics there as well. And this is a problem because we don't really know the health effects that this presence of microplastics could be having on us and on the ecosystems. And this is a problem that matters because it's not really going to go away on its own, and it's really hard for us to go out and resolve since they're so small. So we want to know the magnitude at which it could be possibly affecting us. If you want to learn more about this topic, you could contact me or one of my colleagues, or you could look at our website that's listed below. Thank you so much.
All right, thank you, panel. So now we will open it up for questions. Do we have any questions in the room?
I'm Rich Blaustein, freelance journalist. Thanks for real excellent and informative presentations. I learned a lot. I have a question about biosolids. I gather it's very new in terms of appreciating the problem, but is there any thought being circulated around in water treatment how to treat them?
So just to clarify, like treat the microplastics in the biosolids?
Before it goes into a biosolid fertilizer or anything of that nature.
Gotcha, yeah. So there is a pretty big push probably a couple of years ago on trying to figure out, so wastewater treatment plants became really closely studied because we thought that the effluent, so the water leaving the wastewater treatment plant, was going to be a really big source of microplastics. And as you saw from my study, we found that yes, there are a lot of microplastics leaving the wastewater treatment plant, and they still are, but a lot are also settling into the biosolids. And so there hasn't really been any research that I know of thus far that have looked at treating the microplastics in the biosolids, although there has been some research that looks at kind of trying to find different organisms to break down microplastics. But the problem with plastics really is that there's not really a good way to treat them at this point.
Do we have any more questions for reporters in the room?
Harvey Leifert, freelance. I'm wondering, Emerline, if any comparable studies have been done on natural fibers, wool, cotton, I'm not sure what else, to see if there's a greater, lesser, or equal deposition of fibers into the washing machine, the dryers, and so on, and then into the environment.
You don't feel like it.
Oh, hi. I haven't come across any studies for organic organic fibers, but we did come across with other studies for synthetic fibers. And what those studies shows was that polyethylene sheds the largest amount. But in terms of organic, natural, I haven't come across any studies as yet.
Madeline Nash, freelance. Curious about the biosolids in agriculture, just as an example. And the question I have is, are the microfibers ever small enough to get into things like earthworms and maybe even through the root systems into plants themselves?
Yeah, so there's actually been some really interesting research that looks at how these microplastics are affecting kind of the microorganisms that live in soil, and they are one of the ecosystems that is affected by these microplastics pretty severely. There hasn't been any research on how microplastics might affect plants themselves, though. It'll definitely be an interesting area to look into, I think, especially in relation to agriculture.
I'm Tim McDonald from NPR. Julia, I'm wondering, this may be beyond the scope of the research you've done already, and I know you said it's really difficult, but I'm just wondering if you had ideas about how one might go about trying to clean some of those microfibers up. I mean, what might that look like? Or is that something that's even possible? Or once they're out there, they're out there?
So since these microplastics are so small and they're so widespread and traveling even further, which I was talking about, it would probably be pretty hard to go in and clean up, but what we can do is we can work on preventing our output of these microplastics or microfibers.
Do we have any more questions? Yes, Harvey.
Harvey Lyford, freelance. I wanted to ask Julia, the map you showed near the end of your presentation of 3 areas of the world, the Alps, the Arctic, and California, I guess. And you suggested that there had been transport of these microfibers from one place to the other, but I'm wondering why you assumed that rather than they be generated locally, or more or less locally.
So I wasn't necessarily trying to suggest that they were traveling from the Arctic to the Sierra Nevada mountain range, but more so the locations that we looked in the Sierra Nevada mountain range, they're very remote areas. We chose areas that were at least 150 to 200 miles away from the sampling site that we collected our snow from. So they probably are local in the sense that they're coming from this region, but they're not necessarily being directly deposited into the areas we looked at since they are hundreds of miles away from any human development.
Do we have any more questions? Yeah.
Daniel Stolt, University of Arizona. I'm curious if you have any recommendations or resources what consumers can look at, for example, when I study the labels of body products, shampoos and stuff like that. I find it very difficult to figure out because they don't put microplastics on there deliberately. And same with clothing. Like, for example, are there resources where one can check which type of clothing, for example, is less of concern than others?
With respect to the clothing, I'm not sure of any resources that you can look at. I usually just check the labels, and you want to go for recycled polyester that actually shed one of the least amounts. You want to go, if you're going synthetic, you want to go with recycled polyester. The best thing you want to go for would be cotton, wool, silk. Those are biodegradable. There's biodegradable nylon, hemp. Those are what you want to check for. I usually try to check the labels before. With respect to the pharmaceutical industry, I know that by now there should not be any microbeads within these cosmetics because there was the 2015, the Microbead Free Water Act of 2015. So right now these formulas should not have any microbeads right now.
Do we have any questions on the chat? No? Do we have any more questions in the room? All right, if that's it, thank you so much again to our panel, and that concludes our press conference. So our afternoon is clear for the Bloomberg event. We are going to have a couple of roundtables in the press room at 2 and at 3:30. At 3:30 is our editors roundtable looking ahead to next year. And we'll resume press conferences tomorrow morning. Thanks, everyone.